We are currently working on mixing of two fluid layers of different densities, and they are assumed to have different velocities in the transverse direction. So basically they have shear flow, right? And in case of shear flow, as we have seen, it creates waves, instabilities, and that eventually turns into mixing of these two layers. And what actually happens is, initially it has higher kinetic energy, which converts into uh, potential energy at later time, right? So for this condition we have already derived what is the change in kinetic energy and what is the change in potential energy, right? So we have these two formulas that we have derived. This is delta Ke, that is the change in kinetic energy if this two layer mixes. So that is basically the reduction in kinetic energy that we can put here. And other one is the increase in potential energy. And why potential energy is increasing? Because of mixing, some of heavier fluids are moving up and lighter fluids are moving down. So basically they are acting against the gravity, right? So for these two layers to mix completely and go into this completely mixed zone, right? So let's call it complete mixing. Your kinetic energy must be greater than the potential energy, then only it will be able to bring mixing of the entire layer, right? So in this case delta Ke must be greater than delta Pe, right? Then only mixing will occur. Because if kinetic energy is more in value, then only it will be able to bring majority of a lower layer fluid to the upper layer, and vice versa for the upper layer, right? So this criteria is very much needed. And if this is actually true, in that case we can actually say that this value must be greater than this value, right? Because what you have in the left is the change in kinetic energy due to mixing, and what you have in the right is change in potential energy due to mixing, right? So now if you want to simplify this equation, this will give us this h1 h2 gets cancelled, and what do we get here is this. So u1 minus u2 square, here 2 also gets cancelled, so that must be greater than delta rho g h over rho infinity, where h here is h1 plus h2, a rho infinity is the reference density, and this reference density must be in order of rho 1 and rho 2. This is, let's say, the average of both of them, or in similar range. It cannot be very different different from both the values, right? So this condition, now you see, must be satisfied. And what do you see here is, this is a familiar term which we have already seen in the past, right? And that is the g prime value. So u1 minus u2 square must be greater than g prime h. Okay, if this condition is satisfied, if this condition is satisfied, then mixing will occur on entire depth, right? That is h. Okay, and here you also see that we can actually define, if we bring g prime h over u1 minus u2 square on one side, These actually become something like this. And what you have here is the Richardson number. Okay, so that is another thing that we have studied in the beginning, right, where Ri here is the Richardson number, which gives you the ratio of buoyancy over inertia force, right? So this is something we already did during the introduction of the course. So what it says is, if Richardson number is smaller than 1, then mixing will happen for entire layer. If Richardson number is greater than 1, then it may not happen. However, it is not that straightforward as we think, because when kinetic energy converts into potential energy, or when inertia force converts into buoyancy force, a lot of turbulence gets generated. Okay, in that turbulence, during the turbulence, a lot of frictional losses also happen. Okay, so basically your kinetic energy brings turbulence, which also brings frictional losses in the system. And therefore, entire kinetic energy does not really convert into potential energy. Okay, so there are a lot of frictional losses, and in fact experimental results suggest that experiments suggest that 70% of delta Ke goes into frictional losses. Okay, only 30% of delta Ke convert into delta Pe. Okay, so only 30% of that energy is actually uh, uh, is helping in mixing. Okay, and that is why, while we have got this criteria, this is true only for an ideal case, but in reality that is not really true, and that is why we need to modify this particular criteria and write that zero point 0.3 times of delta Ke should be greater than delta Pe. Okay, and if this condition is satisfied, then we can also write, if we follow the same procedure, this will give us G prime H over U1 minus U2 square should be smaller than 0.3. Okay, so this should be smaller than 0.3, or in other words, your Richardson number is smaller than 0.3. This is the criteria for complete mixing of two layers. Okay, if is greater than 0.3, then only some part of the layers will mix. Okay, so Richardson number must be smaller than 0.3 for complete mixing of two layers. In case if it is greater than 0.3, then complete mixing may not happen. Rather, what happens is there is an intermediate mixing. So for instance, here we are talking about, this is complete H, right? And when this mixing happens here because of overturning of waves, etc., because of the shear flow, only let's say this part of the flow is getting mixed, right? This is now kind of mixed zone. So this let's say this is a small h, okay? It's not completely capital H, and this is smaller than capital H, right? So to be able to find this small h that actually has completely mixed fluids, when Richardson number is greater than zero point 0.3, in that case we can still use this formula that we have derived, that one, to find the thickness of mixing. So in this case, this particular value should be equal to H. Okay, because that is what tells you the mixing depth. So in this case, we basically are indirectly converting these two complete layers of H thickness, capital H thickness, into two layers of small h total thickness, right? So basically the same analysis will now apply for thickness of smaller h. And that is why this h value that you are trying to get, that will be roughly equal to u1 minus u2 square over g prime. Okay, so this is the uh, thickness layer when Richardson number is greater than 0.3. Okay, so this is the layer you will get, which actually is smaller than capital H. And now this analysis that we have derived actually can be applied to any two layers of different thicknesses, right? So we try to derive this for a fixed thickness of capital H, but let's assume that there are two fluid layers which are infinitely thick on two directions, and now you want to find their thickness layer, okay, depending on their velocity and density difference. So this formulation can be used, where we assume that this is uh, not bounded, right? This is also not bounded. So these are open on both upper side and lower side, and this may be just infinitely thick above and below, right? Even in that case, we are able to find the value of h, that is the layer of mixed zone after mixing. Okay, so particularly in the examples that we discussed before, which can be considered as the mixing of sea breeze with the warm air near the seashore, or under the ocean when we have these gravity waves, right? So in these cases we are not able to define what is the fixed boundary at upper side and in the lower side, right? So if there is this cold breeze that is going and hot air that's coming here, and we want to know what will be the thickness h, right? Likewise in this case, let's say there is a mixed zone of capital H after the flow has happened. In that case, we simply need to know what is delta U, that is u1 minus u2, and in this case this can be the absolute value. We don't really worry about this delta U is negative or positive. We need to know the total difference in delta U, and especially if they are going in two different directions, then that delta U will even increase further, right? So we need to know what is delta U and what is the G prime value, right? Where G prime is delta rho times G over rho infinity. So delta rho is again rho 2 minus rho 1, because here we are assuming lower layer density is greater than the upper layer. So delta rho has to be difference between lower layer density versus upper layer density, whereas delta U does not matter, because what we care about is the difference in simply the difference in velocity rather than its direction, because mixing will happen regardless whether the flow is going to the left or to the right. All right. So if we know these two values, then we can predict h using this formula, that is delta u square over g prime. Okay. So this can give you this h value, that is the thickness of this mixing layer. Okay. So this is very straightforward and simple. And now we can also predict the time that will be required for this mixing to occur. Okay, for this thickness of, let's say, small h or capital H. So we can also predict this time based on just the formulas that we have derived. Okay, and that actually gives us, in fact, this should be rather than just calling it equal, we should call approximate, because this is basically we are approximating, and this will tell you the thickness of mixing divided by the velocity of overturn. Okay, so thickness of mixing uh, is simply, we can use delta u square over g prime, right? Because that is depending on whether it's doing a intermediate mixing or complete mixing, the formula remains same, right? It's delta u square over g prime. And velocity of overturn can simply be considered the difference in these two velocity, because this difference is what is acting in the vertical direction, because that we are trying to find basically du by dz, right? So that the velocity is changing in transverse direction, that is what we care about, right? So that, okay, so in other words, what we can actually do here is we can try to predict time based on delta u by delta z, let's say, in that delta u is the velocity in vertical difference in this shear velocity in vertical direction, and delta z is simply the vertical length scale, right? So both delta u and delta z now belong to vertical length scale, or vertical coordinate, and that is why we can simply use the delta u value here. All right, so that will give us, this will cancel this, and the time you get, time will be roughly equal to delta u over g prime. Okay, and once again, delta u is simply u1 minus u2. So again, we do not care whether it's negative or positive, in g prime is delta rho g over rho infinity. Okay, so this will roughly give you the time required for the mixing that we achieve, and this value is usually not very large. Okay, this is fairly small. Okay, so we have seen how mixing occurs in case of a shear flow, and in nature, in majority of cases, we have the shear flow, right? There is two different velocity for two different fluid layers in vertical direction, and here for simplicity we have assumed two layers with originally with sharp interface, so they are completely separate, right, as we considered in this case, or these cases. But in reality, obviously, this is not always true. There is a stratification, continuous stratification. So that is another problem, which however will not cover in this course. But now you have seen how these kind of problems are solved, mixing problem in atmosphere because of shear flow. So you can probably extend this understanding further for an continuously stratified layer by applying some of these basics, and you can try to figure out how mixing and other things happen in the stratified layers, where the density changes continuously with depth. Okay, so we finish the waves, and wave related topic, the instability of waves, mixing due to shear flow, etc., mixing time, mixing thickness. All in the next lecture, we'll start with another topic.